I welcome you 30 days renewable energy masterclass series, and today is a day 30. In this session, we will discuss how to design a MPPT converter with the fuzzy logic controller. And about the Pantech, Pantech is an educational equipments manufacturing company. From Pantech, you can get lab equipments for EEE, ECE, computer science, IT, robotics, IoT related products. You can get it. Our vision is to help 10 million students to learn the technology in easy way. So far, we have trained about 1.5 lakh students. So on this vision, we have scheduled a few more masterclass series, which is going to start from November 15th. If you are interested, you can join there. And about the internship, you can join in the internship. Today is batch 2 is going to end. Today till today midnight, you can join there. If you join internship, you can get all the projects of MATLAB, Simulink, and then you can download the presentations, which is our LMS portal, nothing but like a pantechelearning.com. Once again, I welcome you to this maximum power point tracking converter design using fuzzy logic. So in this session, we will discuss in detail what is the MPPT and what is the basics of fuzzy logic, how we can implement that fuzzy logic converter concepts into our MPPT content, and finally we will discuss the MATLAB demonstration. So in this design, so let us take a solar panel. So this panel will receive a power from the sunlight. So due to this sun process, the sunlight is not a constant behavior, right? So the constant parameter. So due to this behavior, we should always depend the sunlight. So if you want to generate a power from the panel, then you need a constant power, sunlight power. So if it is not a constant, then we have to give a additional facility to draw the power from the panel. So what is that additional facility? That is called power electronic converter. So that converter is going to extract the power from the panel. So how we can extract the power? So by implementing buck converter or boost converter, depends the load, we have to implement with this one. So let us take this block diagram. Yes, this is simple definition, just to go through it. And the main power, maximum power depends these three variables, like the solar radiations and ambient temperature, and then cell temperature. So due to this, the power can vary. So because of this variations, then we are into position to implement this block diagram to extract the power. For example, if you take this block diagram, the load may be either battery or voltage, battery or load, whatever it resistive load. So here, due to the sunlight variations, the power generation by the panel will be vary from 0 to maximum at which the rated power. So now we have to implement one DC to DC boost converter along with the controller. So this controller is going to monitor the panel voltage and then current. So from this it will derive the maximum power. So based on this power, this controller is going to work. So on this process, so now we have to implement a MPPT controller. So this controller should monitor what is the maximum power at maximum voltage. Yeah, the power. There is two conditions. The power drawn by the converter from the panel is a maximum at maximum voltage. So this is the exact conditions to operate or to generate a PWM to the DC to DC converter. So then only we can say it is a maximum power point controller. Or else it's not a maximum power point controller, it's a simple boost converter. So now we are for achieving this one, we are going to use the fuzzy logic controller. So in this session, in this MPPT converter, we are going to use this fuzzy logic controller. So how it can be varied? Here the fuzzy logic is nothing but it's a simple calculating method to identify the exact degree of truth. The degree of truth nothing but here that is this computing method will reduce the sample time as much as possible. And similarly, if you are going to artificial intelligence or machine learning, then further you can reduce the sample time. So everything is the same principle. Only thing, the sample time calculation, that is the accuracy of the how we can increase the accuracy by reducing sample time and the computing method. So this is a very simple method to understand this thing. So now let us take this block graph waveform. See, this is the typical solar panel graph, right? So in this typical solar panel graph, the x-axis is the voltage and then y-axis is the power. So now if you draw the maximum power, so if you take this in this graph, so you can reach the maximum power at this moment. So at this moment, so in this point, the power must be the maximum. At the same time, voltage also should be a maximum, even though the panel generating the maximum voltage than at this point. Suppose if you take this moment, so this is the 30. Let us assume that a 30.2 voltages. Even though you can get a more voltage, 35 voltage also you can get, but at the same time, the power of the power drawn by the converter will be the reduced to lesser value, so than the previous one. So now we have to generate, we have to form a logic to identify this peak value at always. So for that one, we can take a two different point. One is called that is the rate of change of power with respect to rate of change of voltage is greater than 0, right? So this is the one slope, and similarly, let us take it as a positive slope, and similarly. Rate of change of power with respect to rate of change of voltage is less than 0, so that is called a negative slope, and the maximum power we can take it as a 0 value, right? So this is the negative slope, positive slope, and this is the negative slope, and this is the 0 slope. So here during that 0 point we have to which means that during that 0 point we are at maximum power point. So this is simple logic. So the maximum power point we are in the 0 slope, and again for the rate of change of signal, that is a power with respect to voltage, if it is more greater than 0, that is called the positive slope. If it is less than 0, then we can call it as a negative slope. So now in this positive slope, so now each and every sample, so the sample nothing but the equation of the MATLAB model will form as a exponential equation. That equation is solving by each and every samples based on the samples. So now you have an option to vary the sample time. For that one, if you take any one sample, then the next sample will be based on that sample time interval. So if you take a voltage at the nth interval and then voltage at n minus 1 interval. So if you calculate this one, that two voltage between the two intervals, then it is called the rate of change of voltage. Similarly, you can get it as a rate of change of power by multiplying voltage and then current and the same ADC signal. So now, see the positive slope, this variation will be a greater than 0, and then for the negative slope, this variation will be the less than 0. So here, let us assume this point. If you are going this side, again in this positive slope, you are going to take a negative big direction. See here, this voltage variation will be in the negative. So due to this variations of this differences, that is called del V and then del P. So if it again in this positive slope, the variations rises in the negative side, then it is called negative big. So we can call it as a negative big. So in that case, we are going to lose the power. Similarly, if you are going that right side, in this side, this difference will be in the positive one. This difference will be in the positive one. So due to that, we can improve the power. So then we can call it as a positive big. So now we have to difference this sample. So 0, positive big, and then negative big. Similarly, we can have another variable, another side. Here in this negative slope. Suppose if you have if you have calculated the sample difference of power with respect to voltage. Suppose if the difference is positive, power is the positive and then voltage is negative, then we can name it as a positive big and the negative small. Similarly, for the voltage positive and then power negative, then we can call it as a negative big, positive small. So like that, we can name this entire graph. So if you formulate this entire graph, then we needed two main signals. So one is called the power. Ultimately, we need a power, maximum power. So the power and with the sample time. So that is that n minus 1 sample. So now the fuzzy logic can understand the power with respect to the n minus 1th power. So nth power, comma n minus 1th power. So if you apply these two parameter to the fuzzy logic, then the fuzzy logic will automatically calculate these values. So how you can calculate the value? So we have to tell to the MATLAB unit. So if positive zero error, zero error with respect to zero change in error, then we can keep it as a 0 or positive bit. So like that we can implement it. I will tell you one by one. See here in this fuzzy rules. So this is called the error. So there's nothing but that power, del power, right? And similarly, this is the del power n minus 1. N minus 1. So this is the nth sample and then n minus 1 sample. Here, if it is both are negative, NB, then this is the positive B. So these variables will have a this error signal will have a range. So like actually in this simulation, I have used 8 variations. That's the 8 watt I have used, because the 30 wattage can reach up to the power wattage. So the maximum power which we are going to allow in this range. So you can have even 1 wattage also, because if you reduce the range, then you need a more calculating power to your computer. And n minus 1 sample, again in that one range, then the sample will again further it will get reduced. So like that we have to model this range. So here if you take a 0 to 5, here 0 to 5. So the 0 nothing but negative big and then positive big nothing but the 5. So here within this range you have to divide here. So 0 to 1. So like this we have to assign this common two input variables for the fuzzy logic unit, error and then C. So here are the output, these are all the output functions. These are all the output functions. So for that one you can use it minus 1, 0 or minus 1 to 1. So within this range, automatically the rule will get enabled. So now if you apply this one, then automatically we have to add one DC-DC converter, PWM generator to activate that one. See here we have to measure the voltage and current from this block diagram, voltage and current, and we have to apply a fuzzy logic unit. So from this PWM converter, so this converter is going to generate a this PWM pulse is going to activate your boost converter. So now here you can measure the output voltage and then current. So this current, all this power that is called V0 into I0 must be higher than or equal to the ideal power. So it's as much as possible it should be ideal power, equal to the ideal power. So like that we can verify this. So for calculating the boost converter, this is the simple formula. So just use it. So this formula you can use for your applications. And this calculations Excel calculator is available in our website. So you can check in the dashboard. So this is without MPPT. And similarly with MPPT, fuzzy logic we have implemented. So I will demo the fuzzy logic, how it is implemented. Just to open the MATLAB. Here if you apply the fuzzy logic, you can get one window. So this is called the fuzzy window. So this is the fuzzy window. Now you have to import this file. So already I have modeled this one. Just put from file. Put from file. The fuzzy logic. So just to take this function for the fuzzy MPPT. So now this is the two variables. So this is that error value and then change in error. So not a BPP, so it's a change in error. And see here the variations is actually we took 8 voltage is the variations, 8 data, right? Similarly that output that minus 1.5 to plus 1.5, and change in error same values, in error same value. So like that we can take it as a this data. So if you apply this one, then we have to check the value, where rules, on what basis we have modeled. So this is the simple logic which we have implemented. So this is take this logic for this boost converter application. If you follow this logic, then you can easily understand how to implement that one. So for that one, we can change the rules also. So whatever input 1 and then input 2. So here all the parameters will be there. First one and then negative, second one. So like that you can have, and you can just export the graph, put to the workspace, same whatever it is. If you apply that one, then here MATLAB converter, MATLAB file. Just open the MATLAB file. See here voltage of the panel and the current of the panel, and we are taking this current and then voltage, and this is the n voltage, and then and after this block n minus 1 the sample will be there. So if you have this is called a del V, that is the change in voltage. Similarly the change in current. Similarly the change in, if you multiply this parameter, then power with respect to change in power. Power with respect to change in power. So if you take this error, so you say this is called change in power with respect to change in voltage. So this error, if you take this one, this is called error and change in error. So this is the change in error. So now we are applying this two value variable, and if you follow the formula to just here search the fuzzy logic controller in the library block, then you may get this block, fuzzy logic controller. Just to select this one, then you can get this one. Here you have to apply the same variable whatever you have exported there. Then if you then after that this output may vary from minus 1.6 to positive 1.6. So here we are limiting this value from 0 to 1. So you can have it 0 or whatever it is. That is lowest PWM duty cycle must be 0.1. And this is the duty cycle. As per our calculations, we are using the 5000 hertz, 5 kilohertz. We use the Excel calculator to change this value. And after that, there is a pulse which we are going to apply. So if you apply this PWM to this converter, then you can get a variable. So now if you follow the loop, actually the irradiations, since it's a more computing power is required, so I have used a constant parameter. So you can vary the parameter also by using that repeating sequence interpolator. So by using that one, you can use it for as per the previous example, like MPPT or IC, you can use the same parameter, but in that situation, the computer should have a more computing capability to get quickly solved. So this is the output voltage with respect to ideal power. Already I have simulated that variable, simulated functions. So now you can check it. Here we have yes, so this is the 250 is the ideal power, and then generated power by the converter with the help of fuzzy logic controller. So this is within 0.05 seconds it reaches the maximum value, and it's nearly approaches to 250 watts. So like 10 to 15 watts may be a lesser power. Like that we can implement this one. So now you have to take previous two examples and then modify the output, and that is the irradiation. So just to make it as within this signal. So for this time period itself, it will take hardly it will take 15 30 minutes time to solve the the computer is computing power is good, then you can solve it in a fraction of. So try to implement the block same block diagram. take output in the paste the output in the command box. So this is a typical output voltage. The previous methods we have reached for this 250 wattage ideal power, we have reached a similar kind, but somehow it has been improved. Like that, you can implement and paste the output in the video command box. Thank you. I will catch you in the next session. Thank you once again.